Oh, right now. Okay, so I'm recording this now. I wanted to start class just by talking through the first few examples or exercises that I asked you to do for preliminary work involving a handful of these sets and determining whether or not they were, ultimately examining whether or not they were compact. And so I'm going to share my screen here. This is just the set of slides that I lectured over earlier. So hopefully you can see the compactness slides. Let me know if you can't. But I wanted to remind you, there we go. Okay, I wanted to remind you of the definition of compactness and to examine it through the lens of these two sets that we were asked to look at as part of our preliminary work. And those were the sets. I've got this here as a cheat sheet. The set that was the closed interval from 2 to 10, and also the set that is the entire set of real numbers, all of R itself. And so just really quickly, I want to remind you of these definitions, because to get to the definition of compactness, we have to define a lot of extra stuff, right? And feel free to jump in if you have questions or comments or want me to discuss anything in more detail. Feel free to interrupt. So we began by remembering what it meant to talk about a collection of open sets, right? And the idea here was that we had a set of sets. This was our, in this notation here, the O sub i's, those were our individual open sets, and every lowercase I dealt with a new open set O sub I. We organized all of the indices, all of these i's, into some set of indices, and then the collection of all O sub i's such that I was an element of the set capital I, that formed our collection of open sets. And we saw a couple examples of collections of open sets. We then talked about, once we are able to discuss an entire collection of open sets, so a script F, we had talked about what it meant for this collection of sets to be an open cover of some other set S. Namely, F would be an open cover of S if you took your F, you took the union of all of those open sets in F, and whatever that union was, it contained S as a subset. Right, so our F was the set of all of these O sub i's. If we took the union of all those O sub i's and that contained S, we said that F covered S, or that F was an open cover of S. Okay, so then we talked about what it would mean for such an open cover to admit a finite subcover, right? So a script F, which already covers S, admits a finite subcover if there exists a finite number of sets in F that would themselves cover S. And here I'll draw a little picture. I think this is similar to a picture that we might have drawn in class or in the videos, just to sort of illustrate this. So the idea was, if I take my real number line, I have a set S, which that'll be drawn in dark blue. So maybe, try that again, draw that in dark blue. So maybe S is, some subset of my real number line. So maybe it's like those points, and this point, and these points, right? And in blue, maybe that's my set S. We already have a set F, which is an open cover of S. So maybe F, I'll draw that in red, right? So if I have my set script F, that is the collection of all of my O sub i's, right? And so that could be a bunch of open sets. I'll sort of draw them hovering above here, right? But let's pretend there's infinitely many of these. So in my set F, there's infinitely many of these open sets. These should be drawn down on the number line itself, but I'm just drawing them way up here to keep from just looking like an overlapping mess. Maybe there's a single giant open set here. Maybe there's, you know, whatever, 3 here, and maybe there's a lot here. But pretend, and clearly I've drawn just a handful of these, pretend there's infinitely many of these. And taken together, these infinitely many open sets F, these open sets O sub I, the entire collection covers S. Because if I were to take a union of all of these, then that would itself cover the set S. So there's infinitely many red sets, we're pretending. They all cover S, but then we would say that F admits a finite subcover if I can take that infinitely many, that infinite collection of them, I can draw out a finite number of them. So in this case, let's pretend I'm sort of selecting this as my first set. Let's call that, let's sort of rename that O sub 1. Let's rename this set O sub 2, this set O sub 3, and this set O sub 4. Right, so that's O sub 1 through O sub 4. Let's rename this one O sub 5. I'll just take one of these. Let's say this one is O sub 6. And then O sub 7. I wish I hadn't drawn so many of these. Let's pretend this is all 1. Let's say that's O sub 8. That's O sub 8, O sub 7, and let's say O sub 9. So what I've done is I've taken my infinite collection. Again, remember, we're pretending that I had drawn infinitely many red sets, but I'm specifically identifying these 9 green sets. So 9 being a finite number, I have found a finite collection within my set F that, finite collection within my set F that also covers S. So F here, right, this was F was an open cover, and we're at least pretending that it had infinitely many sets in it, or infinitely many elements, each of which is an open set. And we're saying that it admits a finite subcover, because when I take these greens, those greens are going to be a collection of O sub 1 through O sub 9. And the idea is that that is also an open cover of S, but it only has finitely many elements, right? And specifically in this example, we're saying it has 9. So this is a so-called finite subcover of the set F, right? It's finite because there's only finitely many open sets, and it's a subcover because it is a subset of F that also covers S. Okay, big pause. Any questions, comments, concerns, what have you at the moment? All right. Okay, cool. If you do have concerns along the way, feel free to jump in or, type into the chat window. I'm trying to keep an eye on both of those. In the meantime, though, I'm going to erase this picture. Should I erase this picture? Ooh, okay. I'll just keep the picture down here for a second. Okay, so now we get to the definition of compactness. And here's why I wanted to sort of pause and talk about this, because compactness is a challenging definition. Compactness is a definition that would be talking about, in this example, potentially the set S itself, not the open cover or the finite subcover, but it's a property of a set S. So if S is a subset of R, we say that S is compact if and only if, now here's the key phrase, every open cover of S admits a finite subcover. So in this example here, here was my set S. I gave you a particular script F, right? A particular open cover. And we saw by inspection that this F admitted a finite subcover of 9 elements. So this F admitted a finite subcover. In order to definitively say that S is compact, we would have to say that this process could work for every open cover. So not just this F, but every single F that we wanted to look at. Every F, every open cover would have to admit a finite subcover. And that's really challenging to wrestle with, right? That is a really challenging definition, because in order to show something is compact, you would have to show something that it satisfies some property about every open cover. And as we saw in the videos, you can come up with really weird open covers. We're going to come up with a few weird open covers to look at today as part of our daily work. But so as a result, it can be really challenging to wrestle with the definition of compactness or to rigorously show that a set is compact. And so a lot of our work over the next couple days will be towards coming up with a better way to describe compactness. And so because this, I mean, to put it frankly, because this definition kind of sucks to actually work with, you know, sort of in practice, we want to come up with a better way to describe compactness. We want to be able to say, if a set S is compact, that really means that I'm dealing with a set that looks like blank.
Is it pretty simple, though, to prove that a set is not compact?
Ooh, I love that question. Yes, to say that a set is not compact, it can still be challenging, but it's much better. To say that a set is not compact, we would have to say that there exists a finite, I'm sorry, let me back that up. To say that a set is not compact, we would have to say that there exists at least one open cover that does not admit a finite subcover. And that can be challenging sort of on two fronts. Number one, you have to find this open cover, this counterexample open cover, which can be tough. And then secondly, you would have to show definitively that the open cover does not admit a finite subcover. And that's hard to show that something just does not admit a finite subcover. We're going to talk about one explicit example. I think we saw one in the video. We're going to talk about another one right now. But yes, Jesse, and typically it is much easier to show something is not compact, even though that is still challenging. So not to get too far ahead of ourselves. In fact, I'm sort of, yeah, I'm not actually gonna say what I was about to say, but our big goal for this week is to try to work our way up to theorem 8.23, something called the Heine-Borel theorem. I see everybody reaching for your book. You don't have to reach for your book. It's gonna give you a better, it's gonna give you a much nicer way to discuss compactness. Important enough that it is named for the people who discovered it, Heine and Borel. And it is one of our homework questions due Friday. So theorem 8.23. So in a certain sense, if we do our work really efficiently this week, we'll be able to prove that one homework problem collectively in class, which would be cool. If not, you'll still get to prove it for homework, and that will also be cool. We'll be doing a lot of laying of the groundwork so that by the time it comes time to prove it, if we haven't proven it in class, it'll be reasonably straightforward. All right, so that being said, yeah, let's look at an explicit example. This was one of the things that I asked you to look at in your preliminary work. I want to talk about the set R itself. R, the set of all real numbers, feels like it should not be compact. In a certain sense, compact feels like it's supposed to mean small, and R is not small. So our hope is that R is not compact. And we're actually going to prove that. And if you were able to work through, again, there was a fair bit of preliminary work, but if you were able to work through the preliminary work, then you probably saw this already, right? So R is not compact. And here's why. I want to make sure I follow along with the preliminary work. So let's see. So the first thing that you sort of looked at was 8.5. Okay, so exercise 8.5 asked you to create a certain kind of open cover. So exercise 8.5, we went ahead and we looked at sets of the form. So F was something of the form O sub I, such that I was an element of an indexing set. But specifically, we said that in this case, I was equal to Z, right? So I was the set of integers. So our indexing set was the set of integers. And for each integer, for each I in Z, O sub I was equal to the open interval from I minus 1 to I plus 1. Right, so to be really explicit about this, we could say that, just sort of draw this off here to the side, we could say like O sub 0 was the set, the open interval from -1 to 1. O sub 1 was the set from 0 to 2. O sub 2 was the set from 1 to 3. O sub 3 was the set from 2 to 4, and so on, right? And also, O sub -1 was the set from -2 to 0, and so on in the infinite direction as well, right? Each of these lowercase i's inside of our indexing set, which was the integers, so every lowercase I could represent an integer, and every integer had a corresponding open interval, and it was the open interval from that integer -1 to that interval +1. All right, so if we wanted to draw this on a number line, here's my number line, right? And here's a bunch of points on the number line. I've probably drawn it too big, so now I have to draw a lot of points. Okay, so let's say these are our points. Let's say this is the point 0, 1, 2, etc. And then -1, -2, extending it infinitely in both directions, just a standard number line. Then I could draw my open cover. If I wanted to draw such an open cover, I could draw it like this. Right, so this would be O sub 0. It's the interval from -1 to 1. It's centered at 0. Here's the interval O sub 1. Here's the interval, oh, draw it like this. Here's the interval O sub 2. That goes from 1 to 3. All right, and then so on and so on. So we could keep drawing these open intervals like this. Okay, and one thing that, and so what I will claim, this is maybe going back to yeah, sorry, not to get too far ahead of myself. I want to claim that this is an open cover for the set R, right, for our set of all real numbers. So why is this an open cover for R? So claim, I guess, F is an open cover for R. Okay, so how could we check to see that this is true? What are sort of yeah, how do we check to see that this actually forms a complete open cover for R?
If it covers all the elements in R?
Yeah, if it covers all of the elements in R. So what I might say, just to be crystal clear on what we mean when we say covers all the elements in R, scrolling back a couple slides. Yeah, to show that this is an open cover for R, I really want to show that R is a subset of the union of this, all of these sets, right? So what that really sort of looks like is that I want to show, I want to show that R is a subset of the union of all of these I in the indexing set, all of these sets O sub I. And so to rigorously show that, what I would probably do is I would, I think we can do this really quickly. I would say proof. I would take an arbitrary element of the real numbers, and I would want to show that it appears in one of these O sub i's, right? I would want to say that it appears in one of these O sub i's. And I guess to do that rigorously, what I would probably need to do is I would need to find the integer that x is closest to, because x could be an integer, like x could be 1, x could be 8, x could also be something like pi or e, or the square root of 23. So let x be in R, and consider, maybe I wouldn't even take the closest integer. Maybe, have you seen this notation before? Sort of representing the floor function, right? And consider this. This is the integer closest to R, closest to x, but less than x. Right, I guess I just want to make sure. Has everybody seen that notation before? So for example, just pull this off to a different color over here. For example, if you were going to take, so this is sometimes called the floor function. So the floor of pi, right? That's the floor of 3.14 dot, dot, dot. That's going to be the integer that is closest to pi but less than pi, and so that would just be 3. So it's like you're chopping off the decimal point after the number that you plug in. So the floor function, the floor of pi is equal to 3. The floor of the square root of 2, right? The square root of 2 is 1.4 something. So the floor of root 2 is just equal to 1. And if we take the floor of x, then we know that the floor of x is an integer, and x itself is an element of O sub floor of x, right? It'll be an element of that open set. Just to sort of illustrate that on our picture, if I had taken pi, let's say pi is right about here, then the floor of pi, right? I just jump down to the closest integer that's less than it, and that's 3. So that's the floor of pi. And O sub 3 clearly extends all the way from 2 to 4, and so it will contain pi or any other number in that range whose floor had become 3. So what we've done is we've slowed down and we've been able to show that R is a subset of this union because we took an arbitrary element of R, we showed that it was in one of these sets, and since it is in one of these sets, it's therefore in the union of all of these sets. So maybe just to put a bow on this proof, x is in here. So x is definitely in the union of all of these. And therefore, by definition, we can say that F covers R. Okay, so that was, I think that was part of exercise 8.5. How does that sit with you all? Questions, comments, concerns? Okay, cool. All right, well, so this set then forms an open cover of R, but it does not form a finite subcover of R, and that's what's discussed in exercise 8.11. And this is really sort of, well, again, this is beginning to get at the heart of Jesse's question from earlier. So first, 8.11, why does this not create a finite, or why does this not admit a finite subcover of all of R?
Because R is infinite?
Yeah, I think that's really the heart of it. R is infinite, it extends forever. And these sets are all small enough that they definitely won't extend forever. And so as a result, we definitely cannot create a finite subcover. I think
Does it matter if it is countable or uncountable?
say that one more time. Oh, does it matter if it's countable or uncountable?
Yes.
Okay, that's a great question.
I wouldn't think that it would matter, but I just wanted to make sure.
Yeah, I don't
Yeah,
think it
does it-
does. I don't
But does
think it does.
uncountable mean that it's infinite? So if it's
So,
infinite, therefore you can't have finite sets.
so okay, so there is this question about how compactness relates to infiniteness, right? So sort of like, and then when we talk about sets that are infinite, they can either be countable or they can be uncountable. So I'm going to claim at the moment that there are, and we haven't proven this yet, so I'm sort of just throwing this out there and you'll have to trust me for the moment. I'm going to claim that it doesn't matter whether our set is countably infinite versus uncountably infinite. I'm going to say that compactness is measuring something just a little bit different than that. In particular, we will have countable sets that are compact and countable sets that are not, and we'll have countable sets that are not compact, as well as uncountable sets that are not compact. So in a certain sense, yeah, compactness does feel like it's supposed to mean something small, but it'll mean something slightly different than just not uncountable. Okay, but we'll see that. I want to get back to, I think it was Joe that said this, this question of how to rigorously show that this particular open cover does not admit a finite subcover. So let me write that down here. So the claim that we want to make now is that F does not admit a finite subcover. Okay, and I think Joe's answer was at the heart of this, which is that somehow the fact that that the real numbers are infinite plays a role here. And now I want to be careful with how I use this word infinite, because I just got done telling you that infiniteness doesn't really play or infiniteness is slightly different than compactness. When I say that R is infinite, I'm sort of thinking of it as extending infinitely in both directions, while all of these sets really don't extend that far at all. Each of these sets extends, yeah, just a length 2. And so if I took a finite collection of these, there's no way they could cover the infinite expanse that is the real line. So right, so somehow I have to capture that idea.
Can we actually do that using integers, saying something like, because the only time an integer is in the set is if it's the indices, to cover the integers or the set of all integers, we must have an infinite number of numbers because integers are infinite.
Ooh, actually, I kind of like that. So Emily, you were saying that every individual integer is only covered by its own specific open cover. So for example, the number 1, the integer 1, it doesn't fall under this set, it doesn't fall under this set, it only falls under this set.
Yes.
Right? And so every single, every single set contains exactly one integer. Okay, that's not the argument I was going to make, but I like that argument. Let's see if we can run with that. So we could say proof since every, how would you say this? Would you say since every integer I is only contained in one set O sub I? Any finite collection of sets of F, any finite collection of sets in F can only contain finitely many integers. How does that sound? Seems okay? Cool. All right, I like it. I want to offer a slightly different argument, same idea, but a slightly different argument just for flavor, for context, and because, yeah, because I think this other argument might extend to other examples as well. So an argument that I might make here, sort of as a different argument to the one here, might be if we had, so sort of proof, alternative proof, let's say, alternative proof, every, I want to say it this way, if we have a finite collection of open sets indexed by i's, right? So our i's are elements of the integers here. And so if I have a finite collection of these open sets indexed by i's, so that would mean I have an I sub 1, I have an I sub 2, up to I sub n, right? So there's just a finite list of these. Then one of the I sub n's must be largest. One of the I sub k's, I guess, we'll just use all our indices here. One of the I sub k's must be largest. And if I find that maximum I sub k, right? So if I take the maximum out of all of those I sub k's, so the max of the set I1 through In, and I just add, let's say 2 to it, so I take this number, the max of all the I sub n's plus 2, that particular number cannot be covered by the finite set, by the finite collection. Right, so a slightly different argument. I want to make sure we understand both arguments. Here I'm saying if I took any finite collection of these, right, again, I could take the finite collection, I could point out what their indices are, right? Maybe I'm taking the collection like 0, 1, 2, 8, 17. Then I can take that maximum number, that would be O sub 17, or that would be the number 17 in this case. That means that O sub 17 is my largest. I just go a little bit above that, and that cannot be covered by the collection because my entire collection I've established is sort of sitting down here below. So this is an argument that says if I take a finite collection, I can come up with some algorithmic way to identify a point that is not in the finite collection, right? And Emily, I think you could have basically done the same argument, or I think we could have blended both of these arguments to get at your idea, right? That if I had a finite collection of integers or a finite collection of open sets, I have a finite collection of integers and I can construct an algorithmic way to identify an integer that is not covered by the finite set. So does that make sense? This is sort of saying, if I have a finite collection, I can come up with a way to find a point of R that is not in the finite collection, that is not covered by the finite collection. And so the finite collection cannot be a finite subcover. And therefore, our original F could not admit a finite subcover. So getting back to Jesse's question from earlier, this is really how we can show that a set is not compact. And really, we should clarify what we have explicitly shown here. I realize I actually wrote it way back at the beginning, sort of putting the cart before the horse, but we have shown, bam, that R is not compact. And to do that, what we have done is we've taken R, we've taken a particular open cover, that happens to be this one. We have shown that it admits we've shown that this particular open cover actually is an open cover, so it covers all of R. That was the original argument that we had, that we since erased. But we then went on to show that it did not admit a finite subcover through the two arguments that we have drawn down here. So it is easier to show that a set is not compact than it is to show that a set is compact, but even that's not completely easy. I guess it's easier said than done. Any questions, comments, or concerns about this at this point?
I guess the reason that I thought that it would be a lot more simple is because if all of the sets are supposed to admit a finite subcover, then it feels like it should be simple to say, well, if one doesn't work, then.
Yeah, I completely agree. And in a certain way, you're right. It is easier because once we can find that one, then we're good to go. We have found the counterexample that proves the set itself is not compact. In fact, a lot of our work for the rest of today and then all of tomorrow and Wednesday, a lot of our work will be in trying to find sort of very clever Fs, very clever open covers that fail to admit finite subcovers, and trying to come up with a good definition of what particular open cover we want to look at, figuring out what that open cover should be. And that's a lot of the main theorems here. All right, so I want to talk through in slightly less gory detail. I want to talk through one more example. And similar to R not being compact, I want to claim that any unbounded set is necessarily not compact. So I can write this in two different ways. I can say every unbounded set S is not compact. Or I can say what's written in the sheet, which is that if S is compact, then S is bounded, right? And that's going to be 816. Yeah, if S is compact, then S is bounded. So this is another way that we can use compactness, right? It's very hard to show that a set is compact. In fact, I think, yeah, I'm pretty sure over the course of the next few days, we are only going to show that a single set is compact, and that's going to be lemma 822. We're going to show that a single set is compact. A A lot of what we can do, though, is we can make arguments that kind of look like this. If a set is compact, then I can conclude something else about it, right? So if S is compact, then I can conclude something else. And our usual argument for these kind of, well, the usual flow of these kind of arguments are assume S is compact, right? Construct an open cover. Maybe I'll say construct a clever open cover, right? An open cover that is constructed in a certain clever way so that we can derive something from it. Use compactness to conclude that there is a finite subcover. Try to write that quickly. Use compactness to conclude that there exists a finite subcover. And then finally, draw some meaningful conclusion. Okay, so this is another great way to use compactness. If something is compact, then every open cover admits a finite subcover. And if I choose a particular open cover to look at in a clever way, maybe the existence of the finite subcover tells me something meaningful. So we can use this to prove the statement up here, right? The statement that says if S is compact, then S is bounded. And here's our sort of slick proof for doing this. I think this was maybe the final or one of the final questions that I asked you to look at for your preliminary work. Did anybody get this far, get a chance to look at this? Because I ended up giving you a number of these, a little bit. Yeah, yes.
But
Cool.
I did it wrong with
oh,
which you have not said.
that's fair. Okay. But yeah, so let me let's take a look at this. Let's take a look at this. So here's my suggestion. So proof, assume S is compact. So we know that every open cover admits a finite subcover. Let's choose a particular open cover in a clever way in which we can derive something meaningful. So let F be the collection of all open sets of the form negative I to I such that I is a natural number. Okay, so this is going to be the whole argument boils down to choosing this clever F. And to be really clear, right? To be really clear, that means that some of our open sets, like one of them is the set from -1 to 1. One of them is the set from -2 to 2. We have the set from -3 to 3, and so on. I'm going to claim that this set is definitely an open cover of S. So we have to convince ourselves of this, right? It's not an immediate given, but it's a collection of open sets. All of these are open intervals, right? -1 to 1, -2 to 2, and so on. So they're open sets, and every single point on the number line will eventually fall into one of these, right? Because notice, if I took a number line, boop, took a number line and I just start drawing these, right? Here's -1 to 1, here's -2 to 2, here's -3 to 3, right? I could just keep doing this forever. It'd be a lot of fun to watch me. And you know that eventually every single number will get eaten by one of these sets. So in particular, this set is an open cover of S because it is an open cover of R. It's an open cover of every real number. every real number is contained in one of these open intervals, and therefore it's contained in the union of them all. So this is an open cover of our set S. Our set S is compact. So therefore, since S is compact, there exists a finite subcover i.e., right, there exists a list of indices that's like I sub 1, I sub 2, up to I sub n, such that our set S is contained in the union as I goes from 1 to n. Whoops, didn't quite give myself enough space there, of negative I sub, oh boy, index mayhem over here. The sum is k goes from 1 to n of negative I sub k up to I sub k. Okay, but why does this necessarily mean that my set is bounded? Ooh, that's a good question, right? So I've chosen my F, I've shown it's an open cover, I've said that it admits a finite subcover, and here's my finite subcover right here. Why does that mean my original set must be bounded? Let's do a similar thing to what we did before. Oh, I'm sorry, Joe, I cut you off. What were you gonna say?
I was just gonna say, this may not be right, but since it's not infinite, then it would have to be. Yeah, the only way for it not to work is if it was infinite. So therefore, you have to be bounded.
I think you have the right intuition there. Let's tighten up the language slightly. Oh. Let's tighten up the language slightly. But yes, I think you have the absolute right idea there. And I think Mallory does too. Yes, so because our set S is contained in this union here, we can make the observation. This will be very similar to the argument on the previous, the argument that we just made, right? The argument that we just made said that we took the maximum of our indices. We can do a similar thing here. Let's take the maximum. And again, maybe I'm making this more complicated than it needs to sound, but let's take the maximum of all of our I sub k's. Right, so let's pretend that it was contained in the, let's pretend that our set S was contained in the first one, the third one, the fourth one, and the eighth one, or something like that, right? Because we sort of nested these intervals, this means that all of the intervals are contained in that largest one, and that's a bounded set right there, right? So all of this is contained within the total range from the negative maximum value to the positive maximum value of these I sub k's. So if we take the max of I sub k, we could say, and I think I've said this poorly here, let's try this again. I'll say, but the union of all of these k's, k goes from 1 to n, negative I sub k to I sub k, right? The union of all of those is totally contained in the negative maximum value to the positive maximum value. And that is definitely a bounded set. Does everybody sort of follow that? So because all of these sets are themselves sort of nested like this, once I pass to a finite subcover, there's only a finite number of these. That means there's a largest one that contains the rest. And that gives us our lower bound and our upper bound for the set S itself. So that is our big argument here. So much of the sort of power of the argument, right? Much of the power of this argument came from choosing this set right here, this capital F, or the script F. Once we chose that as our sort of choice open cover, then drawing or knowing that S is compact and drawing a finite subcover let us draw some conclusions, namely that it was bounded in this region here. And so the entire set itself was bounded. And a lot of the theorems to come deal with similar tricks, right? Similar tricks. So each of the different groups, I gave each of you a different point to focus on, right? A different theorem or lemma to focus on. And most of the lemmas dealt with setting up interesting open covers. So my recommendation, we're going to split up into our groups for the final 20 minutes to begin thinking through these lemmas. And I'm going to recommend trying to look at your lemma, figure out what it's sort of talking about, and then think about how this could be used in a compactness style argument, which will often come from the following, the theorem that follows the lemma. Our goal being to sort of think through these, do some work today, do some work before Wednesday, do a little work at the start of Wednesday, and then present these big compactness arguments on Wednesday, again, marching towards theorem 823, which will help simplify compactness for us considerably. So those are our goals. I'm gonna pause, I'm gonna stop the recording and I'm gonna pause one more time to see if there are any questions.